Okay, so today's lesson is about fixing common mistakes and misconceptions that students have that lead them to choosing incorrect answers. And this really is more notable in the multiple choice because, again, with the multiple choice, you only have 40 questions, and the grade boundaries for multiple choice are generally a little bit higher than short answer because you're either right or wrong. There's no partial credit, even if you understand the concept 80%, 90%. If the 10% you don't understand is exploited in the question, then you're going to get it wrong. And you'll find your answer on there because the IB is savvy enough that wrong ideas and wrong applications will be answer possibilities on the questions. And so really important that you really have everything kind of nailed down. And so that's what we're going to kind of talk about today, kind of going through the topics 1 through 11 plus the higher level. And I will stick with the same color scheme as before, with SL being kind of the red and orange. And then blue will be HL and kind of, I guess green is HL as well. And so keep in mind when you're going through this that the color kind of tells you whether you need to know or not, because I know there are some SL students in here. So there are things that you don't need to necessarily worry about here. Okay. And again, some of this stuff may sound like common sense and stuff like that, but it's really in the details of the question that I think students get mixed up and they get the wrong answer. And so the first idea we talk about is counting particles, okay? And yes, that's talking about Avogadro's number and things like that, and molar mass, and it seems fairly straightforward, but the way things are asked can be very tricky. And so this is why I bring up this, and I want to talk about what a number actually means, what a value with units actually means. And what I find is that I think students don't necessarily grasp that whenever I write a substance, especially notice I always write units when we do math and stuff like that. If I say 14 grams of CO2, when I say that in an IB question or in one of my questions or a practice, there are 3 components to this number, okay? There is the number, which will change as the units change. There is the measurement, and then there is the substance, okay? And whenever you convert, whenever you're changing, manipulating the number, you can only change one of these things at a time. You can convert grams to moles to particles by using our conversions. And you can also convert your CO2 into like atoms or ions and things like that. But you can only do one of those things at a time. And so students often try to do a bunch of things and they lose track of what things mean in there. And so particles is the same thing as like total, that term total means that. So like if I say, what's the total number of carbon atoms in 14 grams of CO2? Well, the idea here is that you are converting the units for each one in a step-by-step to get there. And this is where that idea of 14 grams of CO2, and I'm going to do it fact label this way, but we can also do a proportional method as well. But your first idea is I need to convert my grams to moles. So this conversion converts my unit from grams to moles, because when I go from moles, I can get to 6.02 times 10 to the 23rd molecules of CO2. And again, this is, I think, where students that don't write units get really tripped up because they lose track of what they're actually talking about. Because if the question asks for total, let's say atoms of oxygen, because they wouldn't do carbon, because a student could not understand the difference between atoms and molecules and still get the right answer. But if they ask about oxygen, then the student will always get half the answer that they're supposed to get because they're not keeping track of their units. And so at this point, you are at molecules of CO2, but the question is total atoms of oxygen. Well, you have the total part. We don't have the atoms of oxygen part. And so what we have to say is that one molecule of CO2 has 2 atoms of oxygen. And that one conversion is the difference between getting the question right or wrong in this idea. And so it's really important that you focus on what your substance you're talking about and what units are applied to them, because it can kind of help you expect what kind of values you want, right? When you're dealing in moles of something, usually it's a smaller number, like ones, tens, things like that. If you're dealing with total atoms or total molecules, you may be dealing with really, really large numbers. But again, they can also find ways to ask you the same thing like this. They might just say, how many atoms of hydrogen are in 2 molecules of CH3COOH? Okay. And the idea here is, what you have to remember is that what we're talking about here is 2 blank molecules of CH3COOH. There's no unit here. There's no grams. There's no moles or anything like that. So when I say I want the number of atoms there, all I'm doing is converting the molecules of CH3COOH to atoms. And we know that there are 4 atoms of hydrogen for every 1 molecule of CH3COOH. So your answer here should be 8 atoms of hydrogen. So it's really important you pay attention to your units and what the question is asking, because this is going to be like the first question on every single multiple choice. Like if you look at all the practice tests, usually the first 2 questions are calculating particles, calculating molecules or atoms, and things like that. And they are fairly easy numbers, because since you don't have a calculator, you're not going to have these super difficult numbers, but still converting them to getting the correct answer is really important. And the answer choice is usually like 2 small numbers and 2 exponential numbers, like scientific notation numbers. And so sometimes you can eliminate some of them, but you still need to consider what's happening and what those units are, because that's really an easy way to make a mistake on this. And so again, why I always stress writing out your units for all of this, because I think you're less likely to make a mistake if you're writing out units that you're actually paying attention to than just writing out numbers that you just assume that you know what the units are. Because again, when you're in a stressful test situation, your mind is running at 1,000,000 miles a minute. And you may think you're thinking of something, but you're also trying to get to the end of the problem at the same time. And sometimes your brain is so focused on finishing the problem that you skip steps in the middle of it to try to finish it faster. And writing stuff down, putting it on paper, making your eyes look at it, I think prevents those things. And that's what we're going to kind of focus on, especially a lot of these issues that students make on this. Are there any questions about this concept here? Okay, any questions, any clarifications that y'all need about this? But I think this key idea here is that understanding the number and what the measurement unit is, and then what the substance is, really will dictate what you get right or wrong. Okay. Questions? Okay. Second thing, okay. Stoichiometry for calculations, because there will be some possible mole-to-mole conversions and things like that for limiting reactants and stuff like that. There are a couple things I want to talk about here with that, and just to kind of make things simpler for you and hopefully kind of prevent mistakes as well. Okay. The limiting reactant problem. Okay. If you're identifying a limiting reactant, okay, what you have to remember is that if you're trying to solve for amount of product being produced, that both reactants have to go toward that product that's being produced. So somewhere along the ways, the calculations become identical, where it doesn't matter at that point. And so if I'm looking for a shortcut for doing this, okay, if I have like A plus 2B yields C, and I want to find which one's limiting reactant, okay, if I have 3 moles of A and 4 moles of B, okay. No, it's okay. If I have 3 moles of A and 4 moles of B, and I want to find the limiting reactant, the easiest way to do that, because what you have to think about is to find limiting reactant, you're trying to see which one makes less of C. And so if you look at this mole to mole ratio, A could make 3 moles of C, and B could make only 2 moles of C. And so B ends up being your limiting reactant in this case, because you can only make a maximum of 2 moles of C because you'll run out of B. But when you're doing these calculations, essentially, once you divide by the coefficient of the original substance, everything else is the same after that. You're multiplying or dividing by the same value, because if you think about it, if you have 3 moles of A and you're converting from 1 mole of A to 1 mole of C, and then 4 moles of B, converting to 1 mole of C, the top part of this problem ends up being identical. So it doesn't actually really matter because you're multiplying by the same value from then on. So if you want a really quick shortcut way to figure out limiting reactant, you take your original amount and you divide. So you divide reactant moles by the coefficient. Smaller answer is limiting reactant. Okay. So if you're just looking for kind of a shortcut to kind of figure out what the limiting reactant is, that's an easy way to do it. Solve for the moles of each reactant and then divide by the coefficient of that reactant. And whichever number gets smaller, that's your answer. Oftentimes students get into this mindset of, oh, whichever one I have less of reactant, that must be my limiting reactant. But that's not always true, because you may need more of this. For example, here, you have more B, but it turns out you need twice as much B to react with every A. So therefore, B is your actually limiting reactant, even though it's in greater quantity. So don't think about just, oh, I have less A or I have less B. It's like, how much B and how much A do I need to use every time I make a C? And in this case, I need twice as much B, so I can only make half as much C, which then makes B my limiting reactant. And so that's kind of a trick that I've thought about here, because the calculations after that are the same. So you can save a little bit of time if you're just trying to figure out things like that. But if you want a foolproof way to do limiting reactant, just take both reactants, solve for one of the products, and whichever one makes less product, that's your answer. So if you don't want to think about other concepts here, just solve all the way to the product, and then just whichever one's in smaller quantity, that's your answer for the amount of product that can be made and what your limiting reactant is going to be. Okay. Questions about that? Okay. Gas laws. Okay. Now, understanding gas laws and things like that, you have a couple of gas laws you need to be familiar with. PV equals nRT, and P1 V1 over T1 is equal to P2 V2 over T2. Technically, it's N2 as well, but usually the moles of gas are the same. Now, this is given to you, PV equals nRT. This one is not. And so there is kind of an understanding that you understand the relationship between pressure, volume, and temperature without like having to have the equation to use for it, okay? And there's two things that you have to really be cognizant of here when you're thinking about gas laws, okay? Well, actually, maybe three if we talk about stoichiometry. One, units, okay? The units of different measurements matter, okay? In pressure and volume, they just have to be the same. It doesn't matter what unit, because the conversions in pressure are multiplicative. So if you convert both of them to kPa or convert them both to atmospheres or convert them both to psi, it's still the same ratio of pressures. If you have 100 kilopascals and 50 kilopascals, well, that's still almost 1 atmosphere and almost half an atmosphere, or it's 14.7 psi and 7.35 psi. So the ratio is still the same. The issue is with temperature, because temperature is not a multiplicative conversion, it's an addition conversion. So therefore, what you think about is when you talk about doubling temperature, you have to think of it as 273 to 546 Kelvin, not 25 degrees Celsius or going to 50 degrees Celsius. Okay, because we're talking about absolute temperature being doubled here. And so there's a huge difference from that. So what the IB does, they'll give you the question in Celsius and they'll say 25 to 50, and you're like, oh, it doubles. But in reality, it's really 298 to 323. So it didn't double at all. It barely increased, maybe 1.05%, 1.05 times. And so that concept and that understanding of the units is super important to avoid mistakes like that, because your units, again, really, really matter in this case. And students will, and you'll find both answers on there. You'll have a variety of answers that fit some misconceptions and things like that. So units for gas laws, super, super important. Temperature always in Kelvin. If there's nothing else you think about with temperature, it's the unit of Kelvin for all your calculations. The only time I think it might not matter is if you're doing change in temperature, where the change in Celsius and Kelvin is the same, so it doesn't matter. But even then, you might as well just convert all the units to Kelvin and then subtract, and then just be on your way regardless. Questions about that? The second thing is stoichiometry of gases. Okay. What we need to understand is that because of Avogadro, he was able to say that all gases at the same temperature and pressure occupy the same volume per mole, meaning that at STP for IB, it's 22.7. Yes, in other places it's 22.4, but for the IB, it's 22.7. So at STP, namely, it's 22.7 decimeters cubed per mole. Now, at other temperatures and pressures, obviously that varies. But what that means is that 1 mole of any gas occupies 22.7 at STP, which means the volume to volume ratio is the same as the mole to mole ratio. So you can save yourself time by just using the coefficients as volume conversions. And so let's say you had something like, I don't know, like CH4 plus 2O2 yields 2H2O plus CO2. If I have 4 decimeters cubed of CH4, and I want to figure out how much water, let's say it's gas in this case, is produced, well, what we can say is that 1 decimeter cubed of CH4 reacts to produce 2 decimeters cubed of water. So therefore, you can make 8 decimeters cubed of water here, and that would work. So you can save yourself a little bit of time on these conversions by just treating volume like moles, but that only works with gases. It doesn't work with solutions in there because the concentration and things like that does vary. So this only works with gases here, is that you could just use the mole to mole ratio the same as you would volume to volume, because it's accurate based on Avogadro's law. Questions? The last thing I want to talk about, oh, this shouldn't be purple, sorry. I just got into the habit of changing colors again, so let me show you. Okay. The last thing with gas laws is the graphs and understanding what these graphs look like and the relationships that are represented by those graphs, and being very careful about axes. Again, like I said in class, axes are an important thing and you have to really pay attention to them because they will dictate the shape of your graph. And so you may understand that pressure versus volume is an inverse relationship, which means that pressure versus volume should get you a 1 over x graph. Okay. But what kind of graph might generate this line with pressure and volume? How would you linearize this? What would you make one of these axes so that you would be able to linearize this graph?
1 over V.
1 over V, exactly. So this would be pressure versus 1 over V. Okay, so they might ask you that as well. The IB might say, which of the following graphs represents, like which of the following relationships represents a direct relationship? And you could say P versus 1 over V is a direct relationship. And so understanding how to manipulate graphs, that's topic 11, but also just a lot of application in this as well. So you have to know how the axes change and how the graph changes with that as well. That's kind of one of the tricky things. The second thing is with temperature, okay? You've got to remember that these graphs of pressure or volume only intersect at the origin if it's in Kelvin, because that's 0 degrees Kelvin, that's absolute zero, and that's the lowest possible temperature that you can record. What you have to remember is that if it's in Celsius, it's the same graph, it's just shifted such that it intersects at negative 273.15 degrees Celsius. Okay, so there's a shift in the pattern here because the x-axis has been manipulated. And so that affects the graphs with that as well. Okay, so understand these graphs and understand how they look similar, but how there are details that are different, and that will kind of avoid any confusion. But yeah, linearizing graphs is a common thing they might do on the multiple choice. They just might give you 4 graph shapes and say which one shows the relationship between P versus 1 over V. And a student will say, oh, P and V is inverse, so I'll just look for the inverse graph. But then you're like, you have to think, well, it's not P versus V, it's P versus 1 over V. And so if V is increasing, 1 over V is decreasing, which is the same thing a pressure does. So therefore it's a linear graph. And so it's a little bit difficult, but you do want to understand that conceptually in this idea. Questions? Okay. Average atomic mass. Okay. Okay. Average atomic mass is the weighted average of common isotopes of an element based on abundance and 1/12 of a carbon-12 atom. Okay, a carbon-12 atom has 6 protons, 6 neutrons, and so there's 12 particles in there that are significant of mass. And so they said 1/12 of a carbon atom is 1 atomic mass unit. This is 1 AMU. Okay, and I only say this because the mistake that I see students make the most, and this is why I present the calculation in a certain way, is that every student seems to think that they can convert percentages to decimals in their head very easily. And that may be true 98% of the time. But for some reason, there's a mental barrier when students see decimal percentages and they just say, oh, it's already a decimal, I don't need to worry about it anymore. And so it's a matter of looking at the idea here. And so what I do for this to avoid that mistake is I take that whole mental kind of calculation out of my head and I just divide everything by 100. So I keep the percentages the way they are. And then just divide everything by 100 at the end. And so that way, I'm not saying, because you wouldn't believe how many times I've seen kids say 0.9% and then you just keep it as 0.9. Because they say, oh, it's already a decimal, I don't need to change it. But that's really 0.009. And that's a significant enough mistake that can cause students to get the answer wrong. But also you should be using some kind of conceptual awareness, because your answer should be between the masses of the isotopes, and it should be favoring the one that has the greatest abundance. And so if you get a number that's out of that range or that's heavily weighted to one side or another, you need to check your work and see what your percentages are and if you're calculating them correct. And so that is a really kind of big thing that students make a mistake on. Now, this is called the average atomic mass. What you need to understand is no one atom has this mass. Okay, no one atom has a mass of 12.01. No one atom has a mass of 32.09 for sulfur and stuff like that. That's an average. And so all masses of each atom in AMUs is a whole number, because that's how you figure out how many protons and how many neutrons there are using that number. And so understand that that average is just something we use as a whole, because we have such large samples that it tends to gravitate toward that value as an average. And that's why we simplify things like that. And so okay. So keep that in mind when you're thinking about this. Okay. Let's see. Okay. Okay. Questions about that? Sorry. I need to make sure I'm kind of consciously kind of waiting here between each idea. Okay. The hydrogen emission spectrum. I feel like it's probably something that we go through very, very quickly and we don't really talk in detail about. But the hydrogen emission spectrum does a bunch of things. One, it discusses that electrons emit photons. There are fixed energies, fixed energy of levels. Okay. And the photons emitted are based on energy level change. Okay. And it's always downward. Okay. So understanding what happens with electrons that allows them to be excited to jump up. And then as they lose that energy, they come back down to their more standard and stable state. And that energy, excess energy, is emitted as a photon. And this concept, this image is really, really important, because there are a lot of details in this idea. And so what you'll see in this is something like this. You'll see n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Oh, sorry. gonna draw it here, so hopefully we'll call this n equals infinity. So understanding this is what happens, okay? An electron gets excited and then it comes back down to its standard state. And in hydrogen, that's generally the first energy level because there's only one electron, so it's constantly moving around and going back down here, okay? Now, a couple of things that were shown in the research with hydrogen emission spectrum. One, the amount of energy that photons had when they were emitted increased as the jump got bigger, but the amount they increased by got smaller and smaller and smaller. So if that first jump of 2 to 1 was, I don't know, 1,000 joules, maybe 3 to 1 was 1,500 joules, and maybe 4 to 1 was 1,250 joules, and maybe, 1,750. Wait, no, am I saying that right? 2 to 1, 1,000, 3 to 1, 1,500, 4 to 1, 1,750, and then maybe 5 to 1 is 1,800. So what Bohr noticed was that the amount of energy it kept increasing by was smaller and smaller. And what that told him was that these energy levels converged. Okay. So what that meant is that the energy levels got closer and closer as they got further and further away from the nucleus, which makes sense because the attraction is weaker. And so they have to get closer and closer, as close as possible to have the attraction from the nucleus. And so that's really important here, that you understand that the energy of the photon emitted increases, but increases by smaller and smaller amounts. And that's how he was able to draw these lines like this instead of just even distributed lines. Because if every jump was the same energy, then he would say, okay, they're all the same individual lines. And he only saw specific lines, which means that you couldn't stop in the middle of energy level somewhere. You had to end up on one. I think the analogy I give is like, this is like a ladder where like you can only stand on one of the rungs of the ladder. You can't stand in between rungs on a ladder. And just imagine the ladder, as you get higher and higher, get closer and closer together in steps. And so it would take you less energy to get up to the next step, but it's still taking more energy from the bottom to get there. Now, this is an emission spectrum because all the photons are being emitted when the electrons are falling back down in energy. An absorption spectrum would be going the other way, where they're going up. And an absorption spectrum shows the light that isn't absorbed. And so you'll see black spaces in the spectrum instead of just the lines that are being emitted. So there's a difference between that. Now, you also have to know that when you jump down to n equals 1, it's UV. Okay. This one is visible. And these jumps down to 3 are IR. So you do want to know what type of radiation, electromagnetic radiation that you're giving off as well. So when it jumps down to 1, no matter where it's jumping from, you're going to see UV, the highest energy of the 3 possible radiation. And then jumping down to 2 is visible, and jumping down to 3 is IR. And what they'll like to do is they'll ask you like how to sketch the relationship here where this is high energy. Actually, I think they'll do low energy here. I'm trying to think of the exact question. Low energy to high energy. And they'll say, what do these 4 look like in this kind of spectrum? And so you would see 1 here, 1 here, and here. The lines would converge at higher energies. Okay. And so that you want to understand as well. That was a popular question in the previous curriculum, but still it's something that you need to understand here, is that you would see the energies converging. And in fact, when you go to, I have this app that is chemistry related that shows you the spectrum. Okay. You can look at hydrogen spectrum, and if you look on the right here, on the very far right, red is the first line. That's 2 to 1. All right, sorry, 3 to 2. The next one is kind of this like kind of aquamarine, which is 4 to 2. The blue one is 5 to 2. And then this kind of violet one at the very bottom is 6 to 2. So you notice at higher energies, the lines are getting closer and closer together. That's representing the energy levels converging closer and closer together. Okay. Questions about that? As you get more and more electrons, it gets more complicated. That's why hydrogen is the easiest one to do that. Like if you start going to other elements, like, I don't know, like cobalt and stuff like that, you'll see because of the D sublevel, because of a bunch of the other electrons that are possible, there's a lot of more ranges of possibilities because of the repulsion and the energy levels that are available. But so hydrogen is very easy because there's only one electron kind of bouncing around and vibrating and emitting these photons. So far, everything's been SL so far. I've been making a conscious effort to stay in the red and orange part through all this. And we'll see a little bit more HL come up in a little bit. But so far, all this stuff is SL. So this should apply to everyone. Electron configurations, okay? With electron configurations, there's a couple of things. I'm going to go talk about the exceptions right now because I think those are really important for this. And that is copper and chromium, okay? Because with copper and chromium, since they're almost half full or almost full in their D sublevel, one of the S electrons moves over to occupy the 3D so that both sublevels are fairly stable. And so Cu will be Ar 4s1 3d10. And Cr, I'm going to write this out completely just to kind of remind y'all. Sorry. Like this. And it's not enough that the IB expects you to know these exceptions. What the IB generally does, the most popular thing they like to do is they ask you about this one. And I think we've talked about this before, but what they like to ask you is about Cu plus ion, because this requires a lot of different aspects to understand to get the entire question right, okay? And so what do you need to know to be able to do this? You'd have to know, one, ions occur when electrons lose from highest sublevel. Not the last one you put in, the highest sublevel, okay? And so the highest sublevel. So in this case, you would lose from 4s first, okay? So you have to know that. Two, you have to know the exception rule of copper, knowing that it's Ar 4s1 3d10. Okay. And I mean, I guess you have to know electron configuration as a whole as well to even get that right, because what they'll do is they'll exploit each of these concepts in their multiple choice. You know, they'll say AR 4s1 3d9, AR 4s2 3d9, AR 4s 2 3d8, and then AR 3d10. Okay. And you can see how each of those choices exploits a misunderstanding, right? Because this kid knew that there was an exception, but took it from the last thing that they wrote versus from the highest energy level, even though they write it that way. And that's why some books do write it this way instead, even though 4s fills before 3D, they write it that way. So that's wrong. This student didn't know the exception and still removed it from the wrong one. Okay. Actually, you know, I guess I could just say like, oh wait, no, the first one is still also the exception as well. So this one, wait, actually, no, I'm sorry. I misspoke. The second one is the actual just normal CU. They didn't take out any of the electrons at all. This one, they took out from the wrong one. They took out from the 3D instead of 4s, and they didn't have the right exception as well. And so it turns out that the answer is AR 3D10. And so again, the IB's goal is to test you on multiple facets of your understanding in the same question. And this is one of those prime examples of that. Understanding multiple things to get a question right on a multiple choice so that students can't kind of stumble across the right answer. This is not about test taking skills, but more about your competency in the content. And so there's rarely times that you can eliminate a lot of answer choices like you would on the SAT or any other standardized tests and things like that. All the answers that you find on there are plausible based on misconceptions and misunderstandings. Okay. Questions about that? Okay. Another popular thing that students, I think, sometimes struggle with is, and this one I've seen show up a lot, I feel like, period 3 oxides, okay? And period 3 oxides accomplished a couple of things very well. One, there are a lot of trends in the period 3 oxides, and these are compounds, and they have reactions that you're held accountable for a lot of these compounds as well. And so these trends include pH of a solution, it includes bonding, it includes connectivity, things like that. So this draws in other aspects without saying, okay, what is connectivity? Because you have to know what connectivity is and then know what type of bonding it is so that you can identify what kind of connectivity it would have in what state of matter. So again, this incorporates a lot of different things, and you'll see a lot of these things being applied. And so you might see, and what I mean by period 3 oxides, just for the record, are your elements in period 3 bonded with oxygen. So the following ones, okay? I guess it's P4O10, P2O5, SO2, SO3, I guess Cl2O, and things like that. Okay. And so understanding, one, how these things behave bonding wise helps you understand how they conduct, okay? And so these, well, let's talk about bonding first, right? So we have ionic, covalent, 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 and covalent. This one's kind of in between, but I think we're going to kind of call it ionic for this purpose right now, because aluminum's kind of a transition metal. I mean, not transition metal, sorry, a metalloid-ish. And so we'll kind of put it in there. But that means our conductivity for ionics only occurs in aqueous, molten, or gas, not solid. Because in solid, all the ions are fixed, so there's no conductivity. Now, these covalent ones have no conductivity because there's no ionization and there's no free moving electrons between all these species. And so that's one kind of key thing with this. Okay, pH, okay, and we'll talk about the reactions of specific ones you need to know here. This one, basic, amphoteric, acidic, and on. So based on the way they react with water or other species, you will see them behave a certain way. So these metal oxides tend to be basic in solution, and non-metal oxides tend to be acidic in solution. And there are certain ones that you have to know reactions to. So you have to know that metal oxides react with water to form the metal hydroxide. Okay. You have to know that some of the non-metal oxides will react to form very common acids like P4O10. SO2 will form H2SO3, and SO3 will form H2SO4. So you may have to justify your reactions here with that. Now, this is not a period 3 oxide, but we'll lump this in as well. NO2, I think we talked about in one of the revisions as well, is you have to know that it is HNO2 and HNO3. It actually splits up into 2 different acids. And that's such a unique reaction. They like to ask about this quite a bit. Questions about this? Does anyone still need a minute to write? I wrote things pretty fast, I know. You don't necessarily have to say anything. I think you can actually just go into like chat and then just like do reactions or something like that. Right? You can like do slow down or speed up or something like that. Thanks, Rick. Okay. Okay. Higher level. The big idea, the first kind of big idea with HL that I think students have trouble explaining are colored complexes, okay? And understanding why these complexes have color instead of why elements emit color when they're electrified. Like this is different than the gas lamps that you had when you electrified them, they give off light. Those are giving off light. These complexes are absorbing frequencies of light, and you see what's not absorbed, what's reflected. So these don't emit their own light. So that means if you put these color complexes in a dark room with no light, they won't appear like anything. It's only when they're exposed to light where they actually are able to absorb frequencies and reflect. Whereas those gas tubes, if you turn off the lights, you will see light coming from that tube. They will be emitting light, okay? And so ideas that you want to focus on, okay? A partially filled D sublevel, because you can't have a full D sublevel and you can't have an empty D sublevel because you have to have electrons moving between the D sublevel orbitals. And so there has to be space for them to move, and then there has to be some of them to move. There is a split D sublevel, okay? where the 5 orbitals now become in slightly different energy. So there is a difference in energy now between the 5 sublevels, 5 orbitals in the sublevel. Okay. Electrons absorb energy as they are excited. So they absorb energy to jump up. Okay. And then the light not absorbed is reflected as a color. Complementary color. So what I mean by that is in the color wheel, there are complementary colors for every one of the 6, for each of the 6 colors that we have. And so you'll see that complementary color being reflected in the system here. Questions about that? Again, that's a higher level. SL, you don't have to worry about that. Okay. Next concept. Electronic versus molecular geometry. Okay. So I think sometimes students mix these up and they don't realize what your options are for each one. Okay. In electronic geometry, all electron pairs are treated the same, meaning that a lone pair has the same effect as a bonding pair in the structure and the organization. So we're not factoring in all the individual repulsions that are occurring between bonding and lone pairs. Okay, so there is a limited number of electronic geometries. Because if lone pairs are treated the same as bonding pairs, that doesn't affect the shape. So really, you only have 3, or in the higher level case, 5 to choose from for electronic. And that will be true for all electronic geometries. And so that would be linear, trigonal planar, tetrahedral. And higher level, you'll need to know trigonal bipyramidal, and octahedral as well. Okay. So those 5 shapes are the only possible shapes that you could have for electronic geometry. Now, molecular geometry, lone pairs have more repulsion. And the shape is only defined by the atoms in the molecule. So while the lone pairs have an effect on the shape itself is really the representation of the bonds in the molecule. Okay. And what I mean by that is that even though lone pairs affect where your starting shape originates for electronic geometry, you slowly take those lone pairs away to affect your shape that's left over from that. And so I think someone asked about this before. It's like, what's the trick for learning all the shapes? And so what I do is this. I draw the following lines. Okay. Okay. These are my 5 electronic geometries. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And the way I think about it is every time I have a lone pair instead of a bond, I remove one of the lines in the shape. And that helps me realize what's left in the shape. For example, if I look at trigonal planar here and I remove one of the lines where it's a lone pair instead of a bond, I get this shape. And that shape is exactly what that molecule is. It's angular or bent. Okay. And if this is 120 degrees, then this is 117 because the lone pair does press it down a little bit closer together. When I do tetrahedral, I take away the top one. So what I have left is trigonal pyramidal. And if I take another one away, I have angular or bent. And if this is 110, then this is 107, and this is 104. Now, with the SL ones, it doesn't matter which one you take away because all the angles are the same. So you're not improving the repulsion or minimizing the repulsion by whichever line you take away because they're all symmetrical in those shapes. So it doesn't matter. In HL, it does matter which one you take away because they're not all equivalent from each other. And so it goes into the idea of removing the bonds that minimize the repulsion the most. And if you look at this, in this shape, the one pointing up is the furthest away from all the other ones. So then you're left with this, a sawhorse or seesaw. Okay. Now, from the other lines, the next pair that's furthest away from the original lone pair is another one on that same axis. And so what you do is you end up getting something like this, a T shape. And then you take away another one and you get linear. So if you just start covering up lines in there, you can actually visualize what the shapes are. Octahedral, take the top one off. Square pyramidal. Now, if the lone pair is on the top, the furthest one away from it is the one on the bottom. Square planar. Now, once you're here at 9 degrees on everything, it doesn't matter. So you just take another one away. T-shaped. Take the opposite one away. Linear. So instead of memorizing, 15, 16 shapes, 5, 9, 12, 13, 14, 15, 15 shapes, just memorize 5 and figure out the ones as you go along the rest of the way. Again, minimize what you have to memorize. Okay, questions? Okay, so that is the shapes and things like that. Now, one thing for higher level in bonding that I find is difficult sometimes is with sigma and pi bonding and identifying how many sigma and pi bonds there are in a structure, because sometimes when the IB gives you structures, they'll give it to you in skeletal form. And so they'll say something like this. And then they'll ask you how many sigma and pi bonds are. And you have to remember that this structure actually is essentially a carbon here with 3 hydrogens, a carbon that's here, and a carbon that's here with 3 hydrogens. And so you have to remember how many bonds there are total. And so here there's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds and 1 pi bond that occurs here. And so looking at the structures, making sure you count every single thing, because every carbon has to have 4 bonds. Okay. There's only one scenario I can actually think of, which is carbon monoxide, where carbon doesn't have 4 bonds. But in organic chemistry, carbon always has 4 bonds, unless it's in the intermediate or something like that. But in a structure itself, it always has 4 bonds. So if you only see 2 lines coming from it, then you're assuming that all the other things that are connected to that carbon are hydrogens. So they're all sigma bonds. Okay. So make sure that you are thinking about that when you look at structures here, because I think that's a very kind of common mistake that students make. with this shape, with these shapes. Energetics. Okay, this with a lot of enthalpy and things like that. Okay, now one of the things just to kind of make sure is that understanding that what this states here, what this reaction states in this problem. And that says essentially that in this reaction, you're releasing 150 kilojoules for one kind of process of this, which means that for every 1 mole of A, you can produce 150 kilojoules, but every 2 moles of B, you produce the same 150 kilojoules. And so really per B, you're only producing 75 kilojoules. So keep in mind that when you're looking at an equation like this, that you treat the 150 kind of like a coefficient for kilojoules, oddly enough. And so you want to think of it as a ratio between the substances, because they might ask you like how many grams of this could make, how much energy would be made from 4 moles of A. Well, 4 moles of A would make 600 kilojoules because of the proportion. But if they said 4 moles of B, that would only be 300 kilojoules because the ratio is 2 to 150 instead of 1 to 150. And that's a really common mistake that students kind of make with this. This next one we talked about in the enthalpy lecture on one of the Saturdays, but this I think is one of those conceptual things that is kind of a higher concept thing, and that's with calorimetry. Okay, and understanding the differences, what you can do to affect calorimetry results, and what can you not do to affect calorimetry results, because the underlying concept is that a reaction's delta H never changes. Doesn't matter how much you're reacting, doesn't matter how little, it doesn't matter it doesn't matter even what like what surface area and stuff like that, you're still going to generate the same amount of heat. Now it may take longer to generate that heat, but it will take the same amount of heat. 2, okay, Q is always related to the water in mass and temperature. And so, like I've said before, a lot of students are so trained and so mentally kind of used to saying that, oh, all the numbers are always given to you directly. And so if I need a grams, I'm just gonna look for grams in the problem. And this is one of those situations where it's not true, because generally they give this to you in volume, and then you have to convert 1 centimeter cubed into 1 gram of water, because that works only for water that 1 centimeter cubed of it is 1 gram. And so they'll give it to you in volume, and the student that doesn't know what they're doing will just take the grams of the reactant and assume that's the grams that you want to use here. But this all has to be of water. And that your delta H is equal to Q of the reaction over the moles that reacted. Okay. And so understanding those concepts and understanding Q is equal to MC delta T will hopefully give you a better understanding when they pose certain questions to you. For example, the most common example is like putting NaOH solid into water and forming NaOH aqueous and trying to figure out the delta H of that reaction. And what they'll do is they'll give you two different beakers, and they'll put 4 grams of NaOH in here and 2 grams of NaOH in here. And they'll have 100 centimeters cubed of water here and 50 centimeters cubed of water here. Okay. Now, when you do this, you already know one value will always be the same because it's the same reaction for both of them. So delta H has to be the same. Okay. Now, what else is going to be the same here? What else might be the same in this scenario? This is kind of tricky, I'm not going to lie. But this is a very IB type of question. Okay. So you have to think about this and think about, well, if I know my delta H is the same, then I can figure out what my Q would be for each of these scenarios. Okay. And we'll call this box A, we'll call this trial B. Okay. Because you're using half the mass of sodium hydroxide here, then the Q of A will be 2 times the Q of B, because you're using twice as much reactant. So you're going to generate twice as much heat because delta H is the same. Okay. But the masses are not the same. Okay. And so if the mass of A of water in A is 2 times the mass of water in B, and Q equals MC delta T, what does delta T have to be? For this to be true, what does delta T have to be? Ooh. Plug in your equations. QA is equal to MA C delta T. QB is equal to MB C delta T. Well, QA would then be written as 2QB is equal to 2MB C delta T. So what does my delta T look like here now that I've looked at those equations? What's my delta T? How are my delta T's for A and B related? Ooh. They're the same. They are the same in value. Because if my Q is double, but my mass is already doubled, then that Q doubled. If the Q of the reaction doubled, that means the water absorbed twice as much heat. But since the water is twice as much mass, that means the temperature change of that water would take the same amount as half the water with half the amount of energy put into it. Because the mass of the water is 150. So I'm putting half as much energy from the NaOH into the system, but I also have much water. So therefore my temperature change is the same. And that's a multiple choice question on the IB. I mean, understanding all of that is what's required. And that's where those 3 or 4 questions that separate a 7 from a 6 happen. This kind of question, where does a student understand what delta H is? Does a student understand what Q is? Does a student understand what Q equals MC delta T means? And then does a student understand what's the difference and what's the similarities between these 2 scenarios, and then dissect them and differentiate them and see what could be the same or different about them. So all of that thinking goes into this one question here. Questions about that? With higher level, a lot of this comes down to units. Okay. And like I've said before in the enthalpy one, your units for this equation here, delta G equals delta H minus delta T delta S, are varied. And a student that is just using the data booklet doesn't necessarily recognize that and may not necessarily think about that. But the IB does give you the units for all the values. It's not like they just assume that you know what the units are. So again, reading the question and writing down the number with its units will save you a lot of mistakes. You know, they say 400 kilojoules per mole for delta H, and they'll say, I don't know, 35 joules per mole per Kelvin for delta S. And if a student had just written down their units when they put this in the problem, there's a better chance that they'd see, wait, one is in joules, one's in kilojoules, I can't subtract this. But kids just go, delta G is equal to 400 minus whatever temperature is 298 times 35. And they just go, okay, I just need to calculate that. And they don't see, because they don't write units down, they don't see where their mistake is because they are assuming that. And if you think your brain is going to automatically always just remember that these units are like that way in a test scenario, you're wrong. You just don't think about those things because you're thinking about, like I said, too many things at once. So everything you can write down helps minimize those mistakes. Be deliberate about things so that you can avoid losing points that you shouldn't be missing. Okay. And so if a kid writes this, it takes a fraction of a second longer when you do that. But then when they do this, they do 400 kilojoules per mole, and then they multiply 298 times 35. They get 10,430 joules per mole. And when you look at that, a red flag should be tipping you off that there is something wrong with this because one's in kilojoules and one's in joules. Now, I'm not saying you're going to catch it every time because you're still going really quickly, but there's a chance that you might see it now going, wait, why do I have kilojoules on one side and why do I have joules on the other side? And what that tells me is I need to divide this by 1,000 to get kilojoules. And then that gets me the correct answer of whatever that value is. And so units are a huge factor in enthalpy and entropy and Gibbs free energy. And they're a cause for a lot of mistakes in there, just joules versus kilojoules. And so really stress that that's an important kind of concept to prevent really big mistakes here. Questions about that? I know we just did this part, but I still think, like, again, for kind of for review later on, the IB likes to also work with reaction energy diagrams because there's a lot of things to unpack in a reaction energy diagram. And there's a lot of things that you have to understand how they vary and how they change based on what you're doing to the system. And so you have your reactants energy and you have your products energy here. Okay. And your difference is delta H. This is the activation of the energy of the forward. Oops, sorry. And this, I didn't draw that line down for enough, is the activation energy of the reverse reaction. Okay. Both reactions are occurring based on that activation energy. And so the really popular question is, what happens when you add a catalyst to the system? And so a catalyst provides us a different pathway and lowers that activation energy. It's whatever the highest peak of that new pathway is for both problems here. What it doesn't change is delta H, because again, delta H is just the products minus the reactants, the difference in that value. And so the catalyst will never lower the activation energy so much that it goes below the amount of products. That's just impossible. Okay. Because then why would you make products if your transition state was lower energy state than your actual products? So there will always be a higher peak there, which is your activated complex or transition state. And so the delta H will never change in that scenario. So manipulating this graph and understanding this is a really key thing for very common multiple choice questions here. And this is another reason why endothermic reactions aren't favored to be spontaneous, because the activation energy of the reverse reaction is actually lower, so the rate of it actually happens faster, and so it's more likely to kind of favor the reactants here. Not always, but often. Questions on this reaction diagram? Again, catalyst provides a different alternative pathway. It may not have to be 2 humps versus 1 and things like that, but you still draw the activation energy from the highest of the multiple peaks down to the reactants and down to the products. So it doesn't matter if the highest peak is the second one or third one or the first one, that's still your activation energy. So make sure you kind of keep that idea in here. And this unit is progress. So it's not an actual real unit. It's kind of more of a visual representation. Your Maxwell-Boltzmann curve. Okay. Higher temperature, flatter curve. Lower temperature, taller curve, but it's shifted to the left. So understand T1, T2, and T3. T1 is less than T2, which is less than T3. And the activation energy can really be placed anywhere in this reaction here for these curves. So understanding where the curves belong to each other, because the area under the curve has to stay the same, because we're dealing with the same sample of particles. So the area under the curve is how many total particles we have. So that shape has to be relatively similar. So if the only way you're going to be able to stretch out that curve is if it becomes flatter. And so that is the key thing that the IB looks for when you're drawing this. Like, is their curve of higher temperature shifted to the right, and is it shorter than the peak on their original temperature? And if you don't have either one of those things, you're going to get docked. The area of the curve should approximately stay the same. Now, it doesn't have to be exact. It just has to show that you made an attempt at it. That's a really common multiple choice short answer question. Sketch Maxwell-Boltzmann curve of temperature 1, and then on the same curve, sketch a temperature T2, which is a higher temperature than T1. So, you too, see ya. Questions about that? Equilibrium. Okay. Couple things that students make mistakes about. The equilibrium constant expression. Okay. The expression, again, has no numbers in it for concentrations. It's all generic. And so if you have something like A plus 2B yields 3C, you'll see C cubed over A times B squared. Okay, so the coefficients become the exponents, and that is what they're asking for when they ask you for the expression. Nothing more, nothing less than that. I guess you could write K equals in there, but that is products over reactants, and with their coefficients being their exponents. Now, K can either be greater than 1 or K less than 1. And so K greater than 1 favors products. K less than 1 favors the reactants. Okay. Now, that's not to be confused with Q. Okay, Q is the reaction quotient. So it tells you where reaction must go to reach equilibrium. So you no longer compare Q versus 1 because you don't care what is favored at equilibrium. You're caring how to get to equilibrium. So you compare Q versus K. And so depending on where Q is, that tells you which way the reaction needs to shift to try to reach equilibrium. If it's equal to K, you're already at equilibrium, easy. If Q is greater than K, you have too much product because the fraction is too large. Q is too big, so you have to make more of the denominator, which is the reactants, to bring the value down. So it shifts left. If Q is less than K, you have too much reactant because the fraction is too small. So you have to make more products by using up some of the reactants. And so then it shifts to the right. Look, even though I've done this for like, I guess 11 years now with the IB and stuff like that, there are things that I don't bother memorizing because I can always figure them out on the fly. There's no point in keeping all this stuff in the memory when you can just kind of think of things. And so whenever I start teaching this stuff and you see me, I pause for a second. Sometimes I'm just going, okay, let me just take a second, make sure that it all makes sense and make sure that I'm able to apply this. And then I present it. And so, yeah, there's something you said about memorization, but like, again, you have a limited amount of space to memorize and you've got 6 subjects you have to do it for. Chemistry is not the only subject you're trying to study for. And so the more you memorize for this, the less effective you'll be in all your classes, right? And so just keep that in mind. Questions? Acids and bases. Okay, couple of things that students mix up. Okay, when I ask for the conjugate base of something, that means it acted as an acid. It seems to be a really kind of weird conceptual thing for students to think about, but if I'm asking for the resulting base, that means the original substance acted as an acid. So if I give you HSO4 minus, the conjugate base is SO4 2 minus, because this acted as an acid and donated a proton and then became SO4 2 minus. So the conjugate base of that is SO4 2 minus. Now, if I've asked for the conjugate acid, it acted, as a base. So therefore, if I have NH3, my conjugate acid is NH4 plus. And it's not enough to think about the charges being like neutral to positive, but it does change by 1. So if you're looking at the conjugate base, it becomes more negative because you're losing an H plus. And if you're looking at a conjugate acid, it's becoming more positive because you're gaining an H plus. But either way, don't just say, oh, it always has to be negative to more negative, or it always has to be 0 to negative. That's not always the case. A lot of different species can act as acid bases, positive ions, negative ions, whatever. So don't think of it that way. Just think about the change in H plus there. Questions about that? pH scale, okay? 1 unit of the pH scale equals 10 times concentration. So understanding that when I change from a pH of 4 to pH of 6, that means A is 100 times more concentrated of H plus ions than B. So whatever the molarity of my B is, A is 100 times that. So if my molarity of B is 0.1, then A is equal to 10. Oh, sorry, 1. No, 10. Sorry, I said that wrong. So 0.1 times 100 is 10. So A would be 100 times what B is. And so without having to do any ice charts, without having to do any, you don't even have to do any like negative log or 10 to the negative stuff. You can just say that if my pH unit changes by 2 units, then that's 100 times change. If it changes by 3, it's 1,000 times. If it changes by 1, it's 10 times. You don't actually have to use a calculator and do negative logs and anti-logs to be able to do that. That's all conceptual stuff. And that's what the IB likes to ask about with SL, because with SL, you don't have Rice charts and stuff like that to do with weak acids and weak bases. So therefore, you don't have calculations that you can do. So this is the way they ask you about those calculations. Now for higher level, the thing that I think that students, there are a couple things that students struggle with in this, okay? One, understanding that acidity is when your H plus concentration is greater than your OH minus concentration, okay? Meaning that it's not always pH of 7 at different temperatures. It could be less than 7. It could be, it could be less than 7, or it could be less than 6. It could be less than 5, depending on the temperature that you're dealing with. And so that concept there, understanding that when you have your 2 concentrations, you could tell whether it's acidic or basic is really, really important, because KW changes. And so the target of neutrality changes with temperature as well. Okay. The second thing is buffers. Okay. And I've had this question a lot, and I know a lot of students struggle with this, is how to make a buffer. Okay. And there are a few things that you need to think about when you make a buffer. And these are the questions you should ask yourself. Do I have a significant source of both, or of let me say this, of a weak conjugate acid base pair? So the question is, do I have a weak acid or weak base with its conjugate in significant supply? It's not significant if I just put a weak acid in there and watch it dissociate, because we know weak acids don't dissociate very much. So that's not a significant source of that. Okay. 2, could I make the conjugate with these solutions I have? Okay. And that's where the tricky part of the buffer, I think, comes into play. And so both those questions are really important. Is there a conjugate acid base pair that's weak, that's involved in my solution? And B, if there's not, is there a strong acid or strong base that I'm given that can allow me to make that? And so you have scenarios here where you can see something like I don't know, 50 centimeters cubed of 0.1 molar HF and 50 centimeters cubed of 0.1 molar NaF. Okay. Now, the conjugate base pair here is HF and F minus. And so do we have that? Yes, we have it here and we have it here. So it doesn't matter how much of each I have, but as long as I have a solution amount of worth of it, it's going to be a significant amount. Where they try to trip you up is they'll say something like 50 centimeters cubed of 0.1 molar HCl, and then 50 centimeters cubed of 0.1 molar NaCl. So if a student doesn't remember that it has to be a weak acid conjugate acid base pair, they see, oh, HCl, Cl, that's a conjugate acid base pair. That must work, but it doesn't because it's not weak. So the addition of the H plus or OH minus would not be absorbed because they're strong and so dissociate again anyways. So that doesn't work because HCl and Cl, not weak pair. And even they could have something like 50 centimeters cubed of 0.1 molar NH3 and 50 centimeters cubed of 0.1 molar, I don't know, CH3COOH. Okay. Well, you have a weak acid and a weak base, but they're not conjugate pairs of each other. So that doesn't work as well. See, NH3 plus 50 centimeters cubed of 0.1 molar HCl. Okay. Now we may be onto something here because we know that if we react these two things together, we can make our conjugate acid when it reacts with HCl. Okay. What's the problem with this combination? What's the problem with this combination? Why does it not work? Because I can make my conjugate weak acid from this reaction. What's the issue? What is our issue here? If I mix these two together, 50 centimeters cubed of 0.1 and 50 centimeters cubed of 0.1. I will have no NH3 left. So there's not a buffer anymore because I don't have a significant source of weak base anymore because I've neutralized all of it with that HCl because I have the same moles of both my acid and my base. So what do I have to do? I have to make sure that I have less acid than base, so that some of it can be neutralized, but then I still have some NH3 left over so that it can react. And it doesn't have to be exactly half. If you want to make a perfectly balanced buffer, then that works. You just put half of a strong acid or a strong base, depending on what kind of weak acid or base you have. That's a really popular question. Now, they don't give you all these choices because there are only 4 choices in there, but they'll mix them up and see. They'll put a strong acid and strong acid conjugate base, strong conjugate acid base pair together, or they'll put the same amount of acid and base together, or they'll put more strong base than the weak acid and stuff like that. So pay attention closely to the values and getting those concentrations and those moles right. And again, yes, if you want to actually calculate the moles of a substance, you do have to convert the volume to decimeters cubed. But right now it doesn't matter, because if they're all in centimeters cubed, you're going to be converting them all the same way. So you can save yourself the trouble of converting decimeters cubed and just multiply the molarity times the volume in centimeters cubed and just compare, because it's all relative. So now if you actually want to figure out the number of moles and stuff like that, that'd be different. But like for this, you can just multiply them together and see which one's the greatest one and which ones you have less of. Questions? For topic 9 and 19, electrochemistry, I think the thing that students, because you haven't ever talked about this until really 12th grade, is that a balanced equation, oops, a balanced equation is one with balanced atoms and charges, because all the balancing you did in 10th and 11th grade was generally everything was neutral. So you didn't have to worry about charges because everything was neutral anyways. And so you just had to balance the atoms and the charges would all work out. Okay. So this is the key part when you're balancing half reactions, things like that, because I think this is where students make a lot of mistakes, because they'll technically balance the atoms and they'll realize they won't think about the actual charge that needs to be balanced here. And so when you're balancing half reactions, you really want to pay attention to that and make sure you're adding up charges right, so you get that thing where it's like Cr2O72 minus yields Cr3 plus, and you have to balance that by first balancing non-H's and O's, then adding enough waters to balance out the oxygens, and then adding enough H's to balance out the waters. And again, students make mistakes here where they're counting the charges wrong, because they forget that this is 14 H pluses, which means it's 14 plus. And this is 1 Cr2O7, which is 2 minus. And this is 2 Cr3 pluses, so that's 6 plus. And this is 0. And so students forget to multiply the charge of the species by the coefficient. And that's where you get a lot of these mistakes where they're not adding the right number of electrons. This one, you have to add 6 electrons here because it's 12 plus and 6 plus, and electrons can only lower the overall charge of an equation. And so keep that in mind when you're doing this, is that pay attention to the coefficients, your balanced coefficients, and make sure that you're looking at that whenever you're calculating charge. Excuse me. That's a really common mistake that students kind of forget about in this. Another thing is with the voltaic cells. These are really common kind of voltaic cell diagrams and talking about what's happening in them. And you have to know, this is a really kind of quick sketch. Our anode versus our cathode. Electrons flow from the anode to the cathode. Oxidation happens at the anode. Reduction happens at the cathode. And so you have to remember those aspects, because if the IB gives you a voltaic cell, they might ask you, what would happen to the mass of the cathode? Well, the mass of the cathode would actually build up because more metals being plated on top of that cathode here in this scenario. Okay. And so understanding the movement of electrons, understanding the anodes, the oxidation, the cathodes, the reduction, those kind of small details here are ones where that students kind of overlook, and they get things mixed up when they're trying to identify on a diagram. And again, the number of electrons being lost and gained should be equivalent. And so whenever you balance these reactions and combine the half reactions together, the electrons should cancel out. But that doesn't affect the potential itself. And if you get a negative value when you plug the voltmeter in, that means you have it backwards. I guess that's another concept that you have to think about is like, if you get a negative value on the voltmeter, that means the electron current is flowing the opposite direction in which you plugged in. So it's going against the grain of your voltmeter. So that tells you that what you thought was the anode is actually the cathode, and what you thought was the cathode was actually the anode. So that's another thing that you want to think about is understanding like the voltmeter is just reading it in the direction in which you plugged it in. So if you plug it in backwards, then you will get negative values, meaning that the reaction that you thought was forward is actually not forward. It's the reverse reaction that's not spontaneous. Okay. Also, for electrolytic cells, remember, for SL, it's molten salts. And they should always go to their elements. So no matter what ionic molten salt you get, just produce the elements. You have MgCl2. It makes Mg plus Cl2. Now the Mg is going from 2 plus, I guess, well, if we're looking at oxidation numbers, plus 2 to 0. So it's gaining electrons. So it's reducing. The Cl is going from -1 to 0. So it's oxidizing. So you would see the Cl2 on the anode and the magnesium on the cathode here. So make sure that you understand that that's a really kind of common multiple choice question as well. Like what are the products, what is the product that's produced on the cathode of the electrolysis of molten salt MgCl2? And so they'll give you a variety of different things in there to see if you really understand what's going on. So you have to, one, know what the cathode does. Two, know what products are made in the electrolysis of MgCl2. And then three, know which of those products is oxidation, which products reduce, so you know which one gets produced on the cathode. So a lot of detail-oriented things to kind of kill a bunch of birds with one stone and testing your understanding. Questions about that? Okay. With higher level, I think the part that's the trickiest is really aqueous solutions. Okay. Meaning that you have the competing water redox reactions. And since you're given those essentially in the short answer with the data booklet, they like to ask about these in the multiple choice. And what you need to remember is that, okay. And so again, oops, 1/2. Here are your reactions. Now, they're not super easy to memorize, but whenever I do this in my head, I'm thinking, well, H plus is going to H2 and O2 minus is going to O2. So that kind of helps me kind of figure out, okay, where are my electrons going to be on the left? When are they going to be on the right? Because if H plus is going to H2 0, that means it's gaining electrons. So you have to put the electron on the left. And if you're going from O2 minus to 0, then you're losing 2 electrons. And so therefore they go on the right. So the idea is that you have the cathode and the anode. So in a lot of aqueous solutions, the cathode could produce H2. Wait a minute. Oh, no, that's right. Because you double, sorry. I was wondering why they were both halves, but I forgot you doubled the top reaction. And so you could produce H2 and O2 as your products in some of these solutions. Like in a dilute NaCl solution, neither Na or the Cl reacts, and so you'll get H2 and O2 as your products. H2 at the cathode, O2 at the anode. Now, with concentrated NaCl, what happens is sometimes what happens is the Cl will oxidize instead of the water, and so then you get Cl2 at the anode here. And so you have to be careful about that. As opposed to the water. And so knowing the oxygen and the hydrogen and where they're produced, and you don't really have to memorize where they're produced, right? Because if you think about water and you think about oxygen, again, 2 minus to 0 is oxidation. So the oxygen must happen in oxidation. H is going from 1 plus to 0, which is reduction. So that has to happen at the cathode. So you can still minimize what you have to memorize without memorizing this whole like thing that I've written here into kind of two major ideas, right? The oxidation number of hydrogen and oxygen, and what happens where in this scenario. Questions on that? I think for organic, that the thing that slows people down the most is visualizing some of these structures that they provide you in this condensed structural formula. You know, I think the thing that I would say is that, let's see, something like this or something like this. Okay. So visualizing what these things mean in an actual expanded structure without wasting too much time drawing everything out. Okay. What you kind of want to see here is anytime you have CH3s bundled more than once, they're not attached to each other because CH3s can't attach to each other, then they become CH2s. So when you look at this structure here, you have to think, okay, all these CH3s are attached to the same C. And then the rest of it is like this. In this one, because I'm writing CH2s together, that just means that they are in line with each other. This one tells you that I can't ever have just a C bonded to an O, then a CH3, because that carbon doesn't have enough bonds then. So what that tells you is that O is now doing double bonding to that oxygen so that it can have 4 bonds. So that O is not in line with the rest of it. It is standing outside. It's double bonded away from the main chain. This here, the OH is bonded to that carbon here. You got to really pay attention to how many hydrogen are on each carbon, because that will help you figure out where things belong. Because if you see CH3, CH2, CH, CH3, well, the only one that's missing something is this one. So it looks like this. Now, this second degree alcohol, because the OH is bonded to a carbon that's bonded to 2 other carbons here. Also for higher level, chiral carbon, because that carbon has 1 H, 1 OH, 1 CH3, and 1 CH2 CH3. So there's a chirality to that. And so there would be an enantiomer here, and there would be optical isomers. Okay. I know Moritz asked about that in class, but not everyone was in that class. And so this is optical isomers. Okay. And I think of all the structures I drew, that's the only one that would have a chiral carbon. Okay, so understanding your condensed structural formula and kind of expanding it out more quickly will help you deal with some of those questions. Okay, And again, visualizing. I would rather you draw them out than just try to look at them and try to mentally unpack them in your head. Because again, when you draw them out, you might be able to catch that you're like, I've seen kids, I'm not sure like how to kind of talk about this, but like, so like we'll have something like C4H8O, and then students will draw it out like this. And they just get into a habit of doing this. And then now when they don't even count to see if they're right. And they just go, oh, everything must have hydrogen surrounding on it. And then they don't realize that this hydrogen is wrong because this makes 9 hydrogens. It's not 8 anymore, it's 9. And so if they do that on the actual test, it's going to be wrong because that carbon can't have 5 bonds. And too many of y'all on your organic tests would do that. And I was a little bit lenient about it, but I should have been stricter about it because that's not right. The structure of it isn't correct. And that causes issues and it doesn't match up with your formula. Again, y'all are rushing to these things and don't go, why do I have 9 hydrogen on here instead of 8? Or why do I only have 7 instead of 8? So drawing it out here, the intent of that is to make sure that you look at it and process what you're doing here. You're not going to be short on time on the IB exam, I promise you. If you have studied relatively well, there may be some problems that slow you down a little bit, but there are other problems that will be quicker than expected, and it all balances out. And I've never had a student that was prepared felt like they didn't have enough time to do the test. I'll just put it that way. Okay. And now if you're not prepared, then you may be wasting a bunch of time trying to figure things out. And that's why you run out of time. But if you're fairly prepared, then there will be some questions that you feel strong with and other ones you feel weaker in, and those time balances kind of balance out. Okay. I think I'll stop there for now. And these are kind of the big things, especially on multiple choice, that I found that students kind of don't think about, and some of the challenging kind of concepts and ways that the IB, quote unquote, tricks you. The IB is not tricking you. The IB is just preying on misconceptions, preying on students that have thought that they can just memorize everything and don't understand what's going on. And so when they're given a problem that looks nothing like they've memorized, they're at a loss for words, or there's an aspect of it that they've never seen before, they can't apply their concepts, and so they can't understand how to do the problem. And that's what they're trying to weed out from the students. They're not trying to see who's the best memorizer. They're trying to see who's the best person to apply the chemistry into scenarios that you may not have seen before. Okay.